But today, Diganta from TCS, he will be giving the lecture. We'll be talking about a tool, okay? There's a tool called Deep Poly. Deep Poly, which is used to verify DNN, for DNN verification. DNN verification. So that's what we'll be covering.
Like, do you have any content?
Yeah, I have. There is a moving for. Yeah, I have a lecture schedule that I can send you in a course description. Yeah.
It's available online.
Yes, I'll share the link. Okay, and that is available online. Hello. Hello. Yeah, hello, can you hear me?
Yeah, I can hear you.
Yeah, let's wait for a few minutes.
Yeah.
Starting slow here, but of course we can't wait for too long either. So 3:40 is what I'll give, so a few minutes, yeah?
Yeah, yeah.
I made you co-host so you could share your screen.
This meeting is being recorded.
Yeah, you can start, Diganta. Hello?
Oh, sorry. I did notice that I was on mute. Yeah. Am I
Yeah,
audible now?
I said you can start.
Yeah. Okay. Thanks. Yeah, let's start. Okay, so this is the lecture on deep poly, which is one of the it is sort of the basis on one of the leading techniques right now, at least according to the VNNCOM benchmarks on
Make
neural
full
network
screen.
verification. I think I am full screen. Is it not?
No, apparently, I'm the culprit here.
Yeah, it needs to be full screen both on my machine and on your machine.
Yeah, now we are.
Okay. So yeah, so this is a lecture on deep poly, which is sort of the starting point for if you want to read and understand what goes on inside the current leading tool, at least according to VNNCOM benchmarks for neural network verification, right? And this is a tool that is in general based on abstract interpretation. Now, I have several slides here that actually go over, abstract interpretation as it applies to neural network verification. But Sir told me that abstract interpretation was covered in quite a bit of detail in class, so I'll not actually spend too much time on these slides. But this is the sort of general
I
picture.
think
Yeah.
I say
Mm-hmm.
there are at least there's a couple of people who might. Yeah, I suggest that you go through those slides. Okay.
Okay. Sure. Yeah, sure.
Quickly.
So,
I
yeah.
mean, maybe not. Yeah, I mean, as fast as you could. So to set the context.
Yeah. Sure. So yeah, I'll just go over them. So one thing that I will say for the people who have seen abstract interpretation before, I am not going to use the language of Galva connections here sort of on purpose, because instead I'm going to present it in a more high level intuitive way that is going to give you all of the things you need to understand to sort of understand what is going on inside deep poly. So I'm not using the language of Galva connections, but those of you who are familiar with that language, you'll be able to relate it to that fairly directly. And for those who are not, you don't need to understand the language necessarily to get what is going on, but know that there is a larger theoretical framework behind all of this, which is called abstract interpretation. And it's based on these things called Galva connections. And yeah, so if at some point you do want to explore sort of a little bit more theoretically, you can maybe read upon that.
Yeah, for
So,
your information, I did briefly cover Galva connection.
yeah. You told me that.
And, kind of quickly went through the relevance of it in terms of what abstract interpretation computes. Yeah.
Yeah.
By the way, I had one question. You have deep poly, comma, crown. Can you,
Yes.
why do you, yeah, can you say something about what crown is about?
Yes, yes, yes. So I'll get to that because these are sort of two separate
Fine.
papers. But their techniques are kind of really similar in that they're all both based on abstract interpretation, and they are sort of the same abstract domain, although slightly different heuristics. And they do ultimately do a few things differently, which is why they are distinct papers. But from the current modern perspective, you can sort of think of the chain of paper that ultimately leads to alpha beta crown. You can sort of choose either deep poly or crown as a starting point. So, with the ultimate aim of building up towards covering at least some amount of what is going on inside alpha beta crown, I thought that in this presentation, I'll sort of club both of them together and present both of them. So initially, we will be talking mostly about deep poly, and that will actually cover a lot of what was proposed in the crown paper as well. And then I'll talk about, okay, what is different that is going on inside the crown paper. So that will be the overall structure. Now, alpha beta crown, as the name suggests, they actually took, if you look at the sort of lineage there, they actually, the same people who worked on crown that eventually started working on alpha beta crown. But yeah, at their core, it's sort of very similar techniques and very similar domains, abstract domains. Okay, so I guess I'll move on now.
Yes, please.
Yeah. So, okay, so I'll give a very intuitive overview of abstract interpretation as it applies to neural network verification, as people in deep poly, crown, alpha beta crown have set it up, right? And if you think about neural network verification, most of the properties that we are interested in are really of this particular form, where we have some precondition on X, and we want to prove that if you pass X through a network N, some post condition will hold, right? So it is of this form of pre-implies post, right? So let's look at that. Just think of that in this layer by layer way, right? So we have X. So this is a neural network, right? And each one of these boxes represents the values happening at each layer. So you have X here coming in, and then it goes into this first layer, right? And then you have values here which are being fed in through the first layer, and then you get some set of values here, which again will be fed through the second layer, and we'll get some set of values x2, which I've not drawn here, but so on, until you finally get some set of values at the output of the network, right? So finally, these are the set of values that goes through the output, right? So you have this sort of layer-wise structure where you have some set of values, a layer operating on them, and then again you get some value and then a layer operating on them and so on, right? So then if you think about the pre and the post, so you can think of the pre, this pink region here is really the pre. This pre is really talking about some set of values at the input before any of the layer has operated on it, right? And then when we apply this first layer, these set of values will get transformed into some other set of values according to the image under the first layer, right? So you have this set, this region of values that represents pre, and then you applied the image of the first layer's operation, and you got whatever this is, right? Of course, the first layer can be, linear, it can be ReLU, it can be some other activation function. Or maybe you are taking a combination of linear and ReLU and calling that the first layer, but in whatever your conventions are or whatever the structure of the network is, this sort of a picture still works, right? So you have this set at the after you operate after the first layer operates, right? And then again you apply this thing again, and you get the second layer, the image after the second layer, and then the image after the third layer, and so on, right? And then finally you get the image at the end, right? So we can call these sets some R0, R1, so on, right? But so you have this pink set at the end, which is sort of the image of whatever this pre is when you apply all the layers, right? That is when you apply the entire network. What you want to really prove is that the post condition holds for all of the points here, right? So no matter what point I start with, if I apply the network, the post condition holds. So post condition should hold for all of these points. Now, again, I can think of the post condition itself as, being a set of values or a region in this space of output values of the network, which is given by this green box, right? So then really what we want to show is that this pink region, which is the image of this pre, is inside this green box, which is this post, right? So that is essentially what we want to show. We want to start with this pre, we want to propagate it layer by layer, and then eventually we'll get some complicated set here. And we want to show that that is inside this post, right? So this is a good strategy. Like start with this pre-prop as a set and propagate it across the first layer. Take an image, then you get this first image, then you take an image again and you get the second image R2 and so on, right? And then finally you get this Rn and you check whether that is completely contained in post. But of course, this is a strategy has got a very huge downside, which is that how do you even represent these RIs, right? Of course, you know, RIs are in general infinite, right? And as you know, I've sort of drawn over here, although this is just a conceptual drawing, even in real life, if you talk about the precise image of even some simple starting set or simple precondition, they can very quickly get very, very complicated, right? Because the entire neural network layer is non-linear, right? As soon as you apply something like ReLU or sigmoid, and then on top of that, you're doing another linear transformation very quickly. I mean, 2 layers down the line, things are going to get very complicated, right? You're not even going to have convexity being preserved. All of the nice properties, linearity, of course not. So all of the nice properties that there may or may not be in your precondition, they'll all be lost, right? So it is really hard to represent these RIs. You can't represent them as lists because they're infinite. You can't also really nicely represent them as formulas because they can be really, really complicated, right? So maybe, you know, you can, maybe you would have thought that, okay, I'll keep track of all of the possibilities here, all of the linear relations, but then as you keep track of them, you'll very quickly realize that you're having to keep track of exponentially many relations and things are getting really, really complicated, right? So this is sort of a general problem with this approach, which is where this sort of abstract interpretation comes in, right? And the key idea in behind abstract interpretation is that, you know, we'll not keep track of this whole complicated set Rn, but rather we'll keep track of over approximations of them, right? That is, we will keep track of these sets AI, where RIs are going to sit inside the AIs. And the key thing about AI is that they should be easily representable, and you know we should be able to do an over approximate image computation for these AIs easily, right? So if you want to keep a picture in your mind, an example of such easily representable sets would be things like intervals, right? So you just say that, okay, I you know, these xi's at any given point can belong to these complicated set of values, but all that we're going to say is that, okay, we don't care about what complicated set of values they're in. I know that the xi's, you know, in each one of these xi's, they're in such and such ranges. They belong to such and such intervals, and that's all I keep track of, right? And you know, that can actually give you a proof. How can that give you a proof? Well, so in this case, let's say that, you know, these deep blue things they're talking about these AIs, right? So you start with the pre, and then you over approximate and you get some AI, right? So this is what you actually represent, this blue box. And then you somehow, now again, if you take an image of this blue box, again, you would get some complicated set over here in AI. But remember, since this blue box contains this pre, whatever this complicated light blue region is after you apply the first layer, it is going to contain R1, right? It is going to contain this more complicated pink region, right? But we are not going to keep track of even this. What we're going to do is we're going to over approximate this at this layer as well and get this second blue box, right? So we start with the blue box over approximating the pink region in the first layer, and then that would lead me to some set of values in the second layer. And we only keep track of a blue box surrounding this second set of values in this layer as well, right? And we do this again layer by layer and so on until we get to the end, right? So again, you do this layer by layer and you get another blue box at the end. And if that blue box is contained in your green box, you're done, right? Because what do we know about these blue boxes is that the pink region, no matter how complicated it is actually contained in this blue box, right? And this blue box is a much more nicer, much more easily representable thing. So you can actually represent it in memory and write code to compute them, work with them, and so on. And now what we know at the end is that, okay, this blue box is actually contained in this green box. And we know that the pink box itself is contained in the blue box. So we know that the pink region, however complicated it was, is contained in the green region, which is what we set out to prove, right? That the image of the pre should be inside the post, right? So this is sort of the general strategy, right? But of course, there's one more piece here, which is that, if you're going to keep track of only the blue boxes, we also need to get a hold of this transformation that takes the blue box in the previous layer and computes a blue box in the next layer, right? And we call that the abstract transformer. So this T is what we call the abstract transformer, right? So again, we started with a blue box over approximating whatever pink region we had in the previous layer. And now if you take the image of this blue box under the layer, you would get some region, some light blue region that looks like this. But conceptually speaking, there is again another bigger over approximating blue box that contains this region, right? And T is supposed to compute that. It is supposed to take this blue box and somehow directly give you this larger blue box that over approximates the image of this one under this layer, right? This is what basically the abstract transformer is supposed to do, right? And then this sort of abstract interpretation based strategy, what it will do is that it will start with an A1, which is, or an A0, which is going to be a blue box, quote unquote, over approximating my tree. And then it's going to repeatedly apply the abstract transformer, right? So you start with this some A0, and then you repeatedly apply this T to AI minus 1 to get AI. And then finally at the end, you just check if this AN is going to be entirely contained in this post condition region, right? So then my abstract interpretation strategy becomes simple. You start with some A0 over approximating my pre, keep applying this T until you get into the last layer, and then check whether this AN is completely inside my post or not, right? Simple enough. But what happens if it's not, right? So what happens if you started with an A0? What happens if you start with a, okay, so I think maybe before talking about that situation, any questions so far?
Okay, no questions. You can.
Yeah, sure. So what happens if you start with an A0 and if you keep going forward and finally, you're in a situation where your AN is actually not contained in post, right? So you started with this blue box, keep applying my T. I got my A1, A2, and so on. And finally, after applying T, however many times, we get this blue box at the end. But see, this blue box is not contained in this green box, right? There is this region where this implication sort of fails, right? So if you try to check this implication, you would actually get a counterexample to this implication, which is represented by this gray point, right? So what happens in this situation? Well, unfortunately, in this situation, we really can't say anything, right? Because remember, all that we're seeing right now are the blue boxes. I've drawn the pink regions, but remember, from our algorithmic point of view, this pink region is really not visible to us, right? So all that we really know from this is that the blue box is not contained in the green box. That does not tell us anything about what is going on in the pink region, which is actually the question that we're interested in, right? It might be that this pink region looks like this, which is that it is contained in this green region, in which case this counterexample is not a real counterexample. It doesn't actually point to the property that we're trying to verify being violated, but rather it is a spurious counterexample, right? Of course, it might also be that this pink region is actually, coming out of this blue box, right? It might be that, the pink region is actually coming out of the blue box like this, right? That might also be the situation, in which case this counterexample might actually be a correct counterexample. But again, just by looking at the blue box, we don't know, because remember, we don't know what this pink region is. It's too complicated for us to actually argue with or understand what this pink region precisely is, right? So we really don't know which of these two situations is the case. And in fact, in general, with this abstract interpretation technique, without doing any sort of refinement, when we get a counterexample, when this property actually fails to hold, when this check actually fails, we don't know. We can't say anything about whether or not the property holds or not. We have a counterexample to this check. That may be an actual counterexample. That may be a spurious counterexample. We don't know, right? And in general, with these papers, Deep Poly and Crown, they actually leave it at this point. They also say that, okay, we won't be able to tell you anything, which is why their technique is what we would call incomplete, right? Because, if it gives you a proof, then it's fine. But if it does not give you a proof, if it can't find a proof, then it can't definitively give you a counterexample to the property, a violation to the property, right? So it's not like this procedure or this technique will always give you an answer. It can actually give you a question mark as a return. Right? It can throw up its hands and say that, yeah, I don't know anything about this. Right? So this is always a caveat that one should keep in mind in general about this technique, abstract interpretation, when used on its own. Later on, we will see a few ways of making it complete. In fact,
just want to make one thing. Okay, so far what he has said is equally applicable to over approximation based thing. Okay, if you notice that Madhukar's was also an over approximated based approach. So these kinds of the concepts are equally applicable. It's just in an abstract interpretation, the domains are specific domains, whereas node merging abstraction was another way of constructing an over approximation, which had a refinement method. Here, there's no refinement. That's all. I mean, here also you could do refinement, but there's concepts called domain refinement, etc. But but we're not talking about those things.
Yeah. So in summary, this particular paper that we're looking at currently at least does not propose any sort of refinement. But yeah, so this general idea of the counterexample, this an over approximation potentially producing this spurious counterexample, which if you don't do any refinement with, will leave you with an incomplete technique. That is, of course, also the case in the node merging situation, right? Yeah. So whereas in the node merging situation, the refinement was one of the focuses of one of the key points of focus in the paper. Here, they don't really propose any refinement. They don't talk about any refinement. Yeah. So this is the current situation, right? Yeah. Now, this was just some terminology that I wanted to introduce. That there's this terminology for abstract domains, but of course, if you're familiar with abstract interpretation, you would know this. But in general, the only terminology that I'm going to refer to in the rest of this slides is there's two things that we really need to craft here, right? So far this is a good template for a technique, but to actually get a concrete technique of this, we need to really specify what these boxes are, right? So far I've been saying boxes and all that, and you could have intervals would be one example of that, right? But maybe there is other ways of doing it. Maybe instead of squares, you could take octagons, you could take polyhedra, you could take various different things. So that essentially is, an answer to the question as to what is this AIs, what are these AIs, and in fact, what is a template for creating these AIs, right? And similarly, we also need to answer what this transformer should do, right? What should this abstract transformer be that takes one of these deep blue regions to this other deep blue region that takes this AI to AI plus 1, right? So what is this TI, right? What is this way to transform these AIs? So if you can answer these two questions, right, together, one template for creating AI, and for that template, a way to transform AI to AI plus 1 by a TI, you would get what one can call an abstract domain, right? And then the rest of this presentation is really going to talk about the particular abstract domain that was proposed by both of these papers sort of simultaneously, Deep Poly and Crown. Yeah, so if there's any questions here, if not, then I'll move to the next slides.
You can go ahead, no? Any
Yeah.
questions? No, please go ahead.
Okay, sure. Yeah, so the next slide is actually, it sort of, I wanted to work through this sort of a framework with the interval domain. Sir, you told me that, this propagation of intervals was something that you had talked about earlier, right?
Yeah, they're actually working. So I've shown them interval propagation and how abstract transformers are constructed, for various operations and so on. So they're actually working on an assignment. Okay, they should be working on an assignment. So I think those things you can assume that you have. So you could, any questions on abstract transformers, where the precision, so the merging of if then else, etc., that I have covered. So you could skip those things. Yeah.
Yeah. Sure. So I'll mostly skip
Unless you
this.
want to include it in your flow of presentation, but you don't need to dwell on it too much.
Yeah. Sure. So I'll not dwell on these too much at all. And in fact, I'll skip through most of this. This is just talking about interval propagation, and I've spent some time talking about interval propagation. Of course.
Yes. Yes.
Yeah. Of course, this is again, as I said, these are things that you've already seen. So I'm going to not think too much about it. But the only thing that I would like to work through simply from a motivation point of view is to apply interval transformation or interval propagation to this particular network and this particular post condition here, just to show you that, okay, this is actually not a good enough domain for certain networks. And the reason for me doing this is because then it allows me to motivate and introduce the actual domain that was proposed in the paper, which turns out it can actually prove this property, right? So what I'll do is, why don't you guys tell me, what the sort of intervals will be over here, right? So we start out with -1, 1 over here. And then I've already written the intervals for x3 and x4. Then, of course, from x3 to x5, I'm applying ReLU, right? So I'm applying ReLU from x3 to get x5 and from x4 to get x6. So can you tell me what the intervals here should be? So is the font, the size of the diagram okay, first of all?
I think it's okay.
Yeah, okay, sure.
Yes.
So can you just quickly tell me what the intervals should be at x5, x6, x7, x8, and so on?
So you're talking about from -2 to 2. So what would
Yeah, so x3,
x5 be?
yeah. So I've already done the interval propagation for x3. So x3 is x1 plus x2 plus 0. So there is a small 0 here representing the bias, right? So x3 is x1 plus x2, so it becomes -2 to 2. Similarly, x4. So now what would x5 be?
Yeah, 0 to 2, they say.
Correct. X6 is also 0 to 2, right? So now what is x7, x8? So yeah, just in the interest of time, I'll just maybe tell you. So x7 is x5 plus x6. So you're just adding things together. So it will become 0 to 4. X8 is x5 minus x6. So again, it becomes -2 to 2, right? So this is okay with everyone?
Yeah.
Yeah, okay, sure. Again, x9 is 0 to 4. What about x10? 0 to 2 again, right? And yeah, so then, okay, quickly, can you tell me what happens for the interval at x11? So x11 is, just to make sure you're seeing this correctly, x11 is x9, x9 plus x10 plus 1. So there's a 1 over here, right? So x11 is x9 plus x10 plus 1.
There's a bias too there.
Yeah, there's a bias there, yes.
Guess it's 7.
Yes, exactly. It's going to be 0 to 7. Sorry, 1 to 7, right? That is fine with everyone, right? Now, of course, with this interval, you can't actually prove this post condition. The post condition is saying that the upper bound of x11 should be 6, right? And you can't prove this post condition with this interval 1 to 7, right? Because if you want to prove this post condition, you would actually, this upper bound here as predicted by the interval domain is actually more than this upper bound 6. So you have a situation where the blue region is actually coming out of the green region, right? So you don't have a proof, right? In fact, if you were to try and check whether or not this interval 1,7 belongs in this post condition, you would get a counter example, right? Which is that counter example being that, value of x11 is 7, right? So here is a question. Is this counter example spurious? Any guesses one way or another? So again, just to give the situation, we did this interval propagation, and you can, I'm sorry if it's going too fast, but you can check the calculations. What you get here is really 1,7, right? And of course, 1,7 can't prove that x11 is less than or equal to 6. All that we're saying is x11 is less than or equal to 7, which is not sufficient. And so, we don't have a proof, but what we have is a counter example. We don't know whether that is an actual counter example or a spurious counter example. So that is the question that I'm asking. The counter example being value of x11 is 7. So is this a spurious counter example? In other words, is it actually possible for this particular network to produce the value 7 at x11?
Yeah, it's spurious because you can't have 4 and 2 at x7 and x8 at the same time, because if you sum those nodes, you'd basically get 2 copies of x3. So the sum should be at most 0 to 4.
Right. Precisely. So if we sort of keep pulling backward, what we should get at x7 and x8 is 4 and 2, which is what you were saying. But for that, we need we are going to basically get a contradiction at this layer, right? Because for 4 and 2 to happen, you need this guy to be 2 and 2 for x7 to be 4. But for this person to be 2, you need x5 to be 2 and x6 to be 0, right? So you have a contradiction at this layer. You can't have 4 here and 2 here, because then you would need this to be both 2 and 0 at the same time, which is going to be a contradiction, right? So of course, I think whoever answered, you talked about the values at this point in the network. Equivalently, I can talk about the values at this point in the network and still prove that this is spurious, right? This same argument sort of works. Yeah, so that is precisely correct. Any questions?
Was that clear? Yeah, there's no question.
Yeah. So really, then this is turns out that for at least this property, this is not a good enough.
Here I just wanted to make one comment. Once again, comparing it to node merging abstraction. See, in the node merging abstraction, you throw the thing at, the underlying engine is Z3, okay? So when you reduce to SAT checks, so in SAT check, there is an advantage. It gives a complete witness as a counter example. It actually gives you the inputs also. So it is easier to check whether it is spurious or not with that counter example, whereas here, that is not the case. Okay, that's why you have to do a little bit more analysis in order to check if it is spurious or not. Okay, so that's the thing. So that's why, one way of doing it was this pulling it back kind of a thing. Yeah.
Yes. Yeah. And I think that is a good point. And I should maybe I'll just briefly talk about 2 points related to this point that's mentioned, which is that one is that, of course, comparing this to the structural node merging based abstraction, and there you need to call some SAT solver, C3 or Madhabu. Of course, the advantage there that says that it's going to give you a complete witness. The disadvantage is, of course, that it's going to take potentially more time, right? Here, even we will see that the same thing holds for the more complicated domain that deep poly and Crown proposes. But even if you think about this interval-based abstract domain, right? The final check of checking whether or not this 1,7 satisfies the post or not is almost trivial. So this entire propagation and the final check can be done really, really fast. These are really simple computations and can be done really fast. And this is maybe a point that I'll stress more later on. Yeah. Even done parallelly.
But here the assumption is that your post condition is also expressed as a domain constraint. Okay.
Yes.
Yeah. So that's the important assumption. So here the assumption is that the input assumptions are expressed as domain constraints. The output property is also expressed as domain constraints. Okay. Then it is easy to check. Yeah.
Yes. Then it's easy to check, and then this entire process of propagation and check both together becomes very easy. But of course, yeah, you do pay that in the sense that you can't really then easily understand whether or not a counterexample is spurious, and you have to do this pullback. And in this case, we were able to do this pullback, but again, in general, pulling back itself might be a little bit complicated, and there are some complexities there as well. It's not always necessarily easy to pull back, because you can run into the same issue of the exact set of reachable points at each at each layer is going to be a complicated set, right? So even when you're pulling back, you might run into the similar sort of issues. So yeah, so this sort of this sort of spectrum is always there. Okay, so this was motivation for why why interval domain at the very least is not good enough. And one key thing that I want to point out is that the reason that at least in our example why it failed is because this x7 was really dependent on both x6 and x5, right? So both x7 and x6 were together dependent on this. Sorry, x7 and x8 were together dependent on this x6, and because they were both dependent on the same variable x6, they were in fact dependent on each other, right? There was some relations between x7 and x8 that makes sure that it's never possible for x7 to be 4 and x8 to be 2 at the same time, right? And those relations are precisely being given by both of them being simultaneously dependent on x6, right? So at least in this example, you can interpret the failure of our interval domain as being because the relationships between x7 and x8 are being lost, right? So by just saying that, okay, x7 is in 0, 4 and x8 is in -2, 2, you are losing all of this nuanced information about x7 and x8, that the fact that they're both, dependent on each other. And in fact, they're both linearly dependent with each other via, x5, x4, x6, and so on. That information is being lost, and that crucial information is what the deep poly abstract domain tries to bring back in to a certain extent, and that is how they sort of try to get a better abstract domain, right? So that is the motivation behind the deep poly abstract domain. Intervals are really fast, but they completely lose all relational information. And then how can we bring back the relational information, but still retain speed to the, this nature of things being really fast to propagate and check to the extent possible, right? So this is what sort of, you can think of the motivation of deep poly as being. Okay. So now I'm going to talk about the deep poly domain, and I'll have some notation here. Just in general, bold variables represent vectors. Whenever you see a bold variable, we are really talking about a vector, right? And the notation for, inside both of these papers, deep poly and Crown, they are a little bit complicated for good reason, because as you'll see that this idea behind each one of these things is really simple. But if you try to write it down symbolically, mathematically, you would have to use some complicated notation. I've tried to avoid that in the slide as far as possible, and instead just explain it to you at a higher level. You can read the paper for all the details. But the basic idea is that, previously we had intervals, right? So if you think about the interval, what are you really doing? You're taking a value of a node and sandwiching it between an upper bound and lower bound, right? So what the deep poly domain says that, okay, instead of just saying that we're going to sandwich it just between an upper bound and a lower bound, instead, we are going to sandwich it between two linear equations. So we're going to have an upper bound, which is actually a linear expression involving some variables in the previous layer. And similarly, we're going to have a lower bound, which is again a linear expression involving some of the values in the previous layer, right? So if you want to keep some picture in mind, this is sort of the picture that you can maybe keep, which is that, if you think about the value of a node at any particular layer, I've called it Zi, the value of this particular node Z, that value changes in some complicated nonlinear way. Again, we're talking about this pink region, right? It changes with some complicated nonlinear way as you change the variables in the previous layer, let's say x1 and x0 in my case. But what we are going to keep track of, so previously what we would really keep tracking of is that, okay, what is the maximum value that this guy achieves, and what is the minimum value that this guy achieves, right? But now we are going to do one step better in some sense. We're going to just keep track of, okay, this region is actually being sandwiched by two linear relations. One linear relation is going to form an upper bound, and again, this is a linear expression in terms of these variables in the previous layers, which, if you want to think in terms of the example, was these x5, x6, x4, and so on. And similarly, we'll have another lower bound, right? So then these upper and lower bound expressions is really what is going to be the representation of my AI, right? And this is basically what we are going to always propagate forward. So instead of propagating intervals, we're going to propagate these upper and lower bound expressions, right? So these are what we keep track of, these expressions. So what are these expressions? These expressions is there's some coefficient corresponding to these variables x and some constant term, right? So coefficient and x for the lower bound. So coefficient and constant for the lower bound, coefficient and constant for the upper bound, right? We also, so that this domain also keeps track of the actual concrete upper and lower bounds as well. Because this is actually required to be able to efficiently propagate these linear upper and lower bounds. Okay. Okay. Yeah. So these LIs and UIs. So this is basically what the previous version would have looked like. This is what we call the concrete bounds.
Yeah, so just to clarify, the concrete bounds are constant bounds before you are deriving. So right now, these bounds are expressions involving the input to the entire neural net, correct?
Yes, yes. So in their paper, particularly in deep poly, they actually do not restrict themselves to input to the entire neural net. They can say that it can be any variable at any previous layer. But
any of the previous layers. Okay.
Yeah. But what they in their implementation and sort of the heuristics that they follow, both in deep poly and cloud, they restrict themselves to the input to the neural network. So effectively, you can just think of it as the input to the neural network. But they present it as being any variable at any given layer. Yeah, and
okay.
Sorry, go on.
Yeah, and I just asked if that was clear. So as a side comment here, which is not okay. See, there are software tools, that use very sophisticated domains beyond interval domains and so on, like polyhedral domain, okay, that he mentioned. But all of them have constant as certain parameters which are all constant, okay. Whereas here it is interval domain, but the parameter, instead of being constants, are expressions, symbolic expression. That's the kind of the twist here. Okay.
Yeah. So in some sense, it is. Yeah. So if you want to put it in the precise language of abstract interpretation with Galva connections and everything, you'll have to sort of, the way that the deep poly paper does it is that they define it as an relational domain involving all of the variables, and each time one more layer sort of gets processed, they add they sort of treat it as if you're adding a bunch of new, declaring a bunch of new variables in your quote unquote program, and then these expressions then define sort of a relational domain for that new variable. But yes, this is I think a really interesting point, which is that people have tried other domains, more complicated domains, zonotopes, octagons. The references are there in the deep poly paper. They compared two tools which did that, and polyhedra and all of that. But then the key difference is that all of these domains, none of them really thought of keeping track of the values of the allowed values of the current layer variable in terms of the input to the neural network, right? And that is something that is actually fundamentally new or unique, one can say, about both deep poly and
thing is that it's not clear. Okay, so I think in the neural network context, I think this is not only efficient, but it's also increases expressibility beyond interval domain. Now, a relational domain, it may get some of this expressibility, but at an enormous cost. Okay, because these relational domains, like polyhedral domain, etc., building abstract transformers, the abstract transformers are fairly complicated, okay, and therefore are not as efficient. And I think this is a sweet spot that these people have, I believe, have worked out, that seems to do reasonably good job for in the context of neural network verification. That's my intuition. Okay, so I just wanted to add my 2 cents worth there. Yeah.
Yes, definitely. That is definitely what the idea that. So one thing that is that when I mentioned relation depends with respect to the deep poly paper, they are just using that as a language. They're not, really. Yeah. So maybe let's not confuse the point further by going there. But if you were to do something like keep track of polyhedra and propagate that will involve things like convex cell operations.
Convex
to-
Hall.
yeah.
quite-
Okay. So even if you don't know what convex cell, they are really complicated operations involving multiple calls to optimization algorithms like LP optimization algorithms and so on, which are expensive, right? The key thing about the deep poly domain is that it is almost as fast as interval domain, right? And it is almost as simple to code up as interval domain, and that makes a huge that is hugely important, because later on some of these tools they were actually able to parallelize it massively over the GPU, right? And that allows you to scale this up in a way that was previously really not possible. Yeah, but okay, so over here in this diagram, this is the point that I've already made, which is that the key point here is that it's somehow capturing more relations between variables. But again, it's not by by making a more complicated domain. It's by really saying that, okay, look, we are going to say that the variable x7, the upper and lower bound of this is actually being given in terms of variables in the previous layer, x5 and x6 in this case. Of course, you can go further back, but that is the idea. Right? Okay. So now how do you actually design the abstract transformer for this, right? So we have said what these A's will be, what is the template for A's. Now we need to talk about what the T's will be, coming back to our previous notation, right? So for the abstract transformer, mainly right now, the two things that I will talk about is linear layer, and then I'll talk about ReLU, right? So linear layer is actually fairly simple, because see, if you talk about linear layer, any linear layer is anyway linear, and what you're saying is that you're going to bound the value of this particular variable in terms of linear expressions coming from the previous layers, right? So you can just say something like what I've written in this diagram. So for example, here x7, there's a linear layer that is feeding that is deciding what the value of x7 should be, right? Given by this 1, 1, 1, -1, and so on, right? So we can say that, okay, look, x7, the value of x7 is basically just between x5 plus x6 and x5 plus x6, right? So it's almost trivial, right? It comes directly. And then again, if the variables that you're taking in this x is x5 and x6 itself, then over here directly you're done. But what you can do is you can then back substitute x5 and x6 in terms of more relations of this form, right? So you will have some relation where say x5 is between some relation involving x4 and x3. X5 is again less than equal to something, some x4 times something plus x3 times something, and so on. And you can substitute that into here. And similarly, you can substitute the upper bound for x6 into here, upper bound for x6 into here, lower bound for x6 into here, right? So if we had some relation that said something like, let's say, x5 is less than equal to, or sorry, greater than equal to 3x4, just for an example's sake, plus 2x3, and between again 5x4 plus 3x3, let's say, then you can substitute this guy into here and get a relation involving x4 and x3, get an upper bound involving x4, x3, and x6. If you have another similar bound for x6, you can substitute that as well, right? So this is the sort of idea with what you do with linear layers. You can just take the relation, the direct equality relation coming out of linear layers as your bounds. And if you want to keep a relation in terms of these variables, then immediately you're done. If not, if you want it in terms of some variables coming from the previous layer, or let's say in terms of the input to the neural network, the input, by input, I mean the input layer itself, the actual inputs to the neural network, then you can just keep substituting recursively until you get it, right? Yeah. So yeah, I mean, it is in principle similar to intervals in that what you're really just doing is just substituting, right? Yeah. So now any questions here, Todd, before coming to
You
it?
can go ahead.
So
No
the really the non-trivial part of any abstract transformer really for neural network verification will come when we try to handle the non-linear parts of a neural network, which is the activation functions, right? So what do you do for these activation functions. So let's take ReLU. So ReLU is really the first activation function that most people focus on, and what at least Deep Poly very explicitly focuses hard on ReLU, although they talk about other activation functions as well, right? So what do you do there? So again, remember that you have some concrete lower and upper bounds, right? So if you think about ReLU, ReLU is what? ReLU is some expression that looks like this, right? You have some input to your ReLU and you're calculating some output, right? So what they would basically do ultimately is give some bounds on this Z, on this output Z of the ReLU in terms of the input of the ReLU X, right? So once you have those bounds, and then if you had some bounds of X coming from some previous calculations, something that looks like this, you can again substitute and so on, right? So what we really want is some linear bound on Z in terms of X, right? Now, again, remember that we have some concrete lower and upper bounds for X. As part of our abstract domain, we're keeping track of these Li's and Ui's, and this gives us some concrete lower and upper bounds for X, right? So immediately what we have is sort of three cases. First two of these cases is immediately trivial. So the first case is what happens if both the concrete lower and upper bounds of X is below 0, right? So then what are we saying? We're saying that the input to this ReLU is always less than 0. So then what is the value of ReLU? Value of ReLU is always 0. So directly we can just write this, right? And this directly just gives us the abstract value for Z, right? Similarly, if ReLU is always active, that is, if the input to ReLU is always positive, that is, if the concrete lower bound is always greater than 0, concrete lower and upper bound both are always greater than 0, then again, the output of the ReLU is just going to be exactly the same as the input. So you can just directly say this, right? So these are two trivial cases. The really, the interesting case is when the lower bound is less than 0 and the upper bound is greater than 0, right? So what do you do there? So what they do here is actually an idea that I've seen referred to as a triangle approximation in other places, which is actually common to both Deep Poly, Crown, and a few other works and many other works down the line, which are based on Deep Poly and Crown as well. And the idea is this: for the upper bound, what they do is they take the point where sort of you hit this concrete lower bound, and you take the point where you hit the concrete upper bound, and you connect them, right? So you consider this sort of a line, right? Notice that this line within this sort of interval of input values, this line is always going to be greater than whatever the value of ReLU is, simply because ReLU is a convex function, right? So this is always a line that you can take as an upper bound, right? But what about lower bounds, right? So for lower bounds, what they say is that you have two choices. So you can either take this line, which is X equal to 0, right? Or you can take this line, which is X equal to X, right? So this is one potential lower bound that you can take, and this is another potential lower bound, right? So notice that if I take this upper bound and either this lower bound or this lower bound, I always get a sound linear upper and lower bound for my ReLU. Why? Because I always know that my X is in this interval. And then if I take either these two lines, they sandwich this ReLU curve, or these two lines, they also sandwich this ReLU curve, right? So both of these are actually valid choices for me, right? For taking a linear upper and lower bound.
Yeah, just I want to make sure. So he used the term legal sound. Okay, is that clear? Why both of them are sound? Okay, because they include all the real values and some more maybe, but never exclude any of the values that have to be included. That's why they're sound. Is that clear? Yeah. Okay. Go ahead.
Yes.
Go ahead. I just wanted to emphasize it.
Yeah, sure. Yeah, so that is true. I mean, this is they include all the actual values that you can take, like for any particular potential value of input value of X on this line, the actual value that you can take is going to be on this sort of a curve, right? So for this sort of an input X, Z was ReLU of X, so Z can be this particular value. So then if you look at the pair of X, Z values, it's going to be here. So similarly, this is also an actual pair of X, Z value. And all of these actual values, all of them lie between both of these lines. So all of the actual values are covered. And of course, if you take, for example, these two lines, some other values are covered, which is, these values which are above this line and these values which are below this line, right? So some extra values are being covered, which is, why this is an over approximation, which is how you're actually losing, which is what you're losing by taking an over approximation. But it is nonetheless sound in which that, in the sense that you're not missing any actual values, right? Yeah. So we have two choices for the lower bound, this and this. So then what it really comes down to is choosing between either this or this, right? So upper bound is always going to be the line joining these two endpoints, if you will. And then lower bound is going to be a choice. Either you take this line or you take this line, right? But which of these two do you take? So again, what we really want to do is we want to take one that where the number of over approximate values is minimized, right? So we want to take a line where the number of values that is sort of not actual values, but is still being captured within an over approximate region. We want to minimize the number of such values, right? So what this both deep poly and Crown suggest as a heuristic for doing this is to look at the areas of these two triangles, right? So let's consider the two cases. So we have this case, right? So here, the actual values are all on this line. Everything that I've shaded here is actually an over approximate value. And if you consider, if you're taking these two things, then everything within this triangle is also an over approximate value, right? Similarly, in this case, everything within this triangle is an over approximate value. Everything within this triangle is an over approximate value, right? So in both of these cases, this triangle, all of the things inside this triangle, which is marked with this sort of light blue lines, no matter what you do, all of the things within this triangle will always be inside your abstract domain, right? So abstract values. So no matter what you do, all of the values in this triangle will sort of be carried forward as some additional values other than the actual values, right? But the choice between this line and this line, what it really lets you choose is whether you want to also keep the values inside this triangle or the values inside this triangle, right? So now you remember that you're trying to minimize the values, the extra values other than the actual values that you're going to carry forward, right? So essentially the lines that you will choose is going to be either this line or this line based on whichever triangle has minimum area. So that is the heuristic that they propose. So if this triangle has got a lower area, you choose this line. If this triangle has got a smaller area, you choose this, right? And in that sense, in that way, basically between these two lines, you choose the one that minimizes the area of the two triangles the most. Okay. So yeah, so in this case, this is the blue region. So that's basically this triangle plus this triangle versus, sorry. Yeah. So versus the other situation. So in this case, actually, this was the best choice, right? Yeah. So one point that I will quickly mention is that when we're making this sort of choice, again, what we're really doing is we're trying to design heuristics that, while maintaining soundness, maximizes tightness, right? And this is again a sort of common theme across abstraction, not just abstract interpretation, but abstraction in general, is that you want to, unless there's some huge additional cost, which in this case, there is no additional cost. Like both of these two lines are exactly going to be the same cost, right? Unless there is no additional cost, you always want to choose something which is as tight as possible, right? So you want to make sure things are sound. And then really so that is always a hard constraint. And then really what the other constraint that you have is this sort of push and pull or spectrum between making things tighter and costlier, right? So in this case, actually, both of these two things are equally, free of cost, they equally have very low cost. But one can be potentially tighter than the other. So we always choose the tighter. So this is again a general principle. Yeah, and again, as we were doing before, once you have these bounds, again, remember that this is basically a linear bound on the output of the ReLU in terms of the input to the ReLU, right? And then you can again always, so that is going to be in terms of the immediate previous layer. So if you want something in terms of layers before that, you can always keep back substituting and keep going back and so on. Right? So that is what I mean by substitute. And you'll have to also calculate the concrete bounds. So you calculate concrete bounds by saying, okay, if this is my linear bounds, then I'll substitute the concrete bounds for these variables here and then do the interval propagation on top of that, right? So you calculate your concrete bounds, Li and Ui. Yeah. So this is what they propose to do for the loop. Any questions? I'll.
Yeah, yeah. There's one question here.
Yeah.
Are LX and UX also in terms of the previous variables, or?
No. So Li, Ui, you mean, right?
Yeah.
So these two things, they are not in terms of, so these are scalars and these are fixed constants. The only reason that they keep, so technically you don't really need to keep track of this. You can sort of do an intermediate step where you always keep recalculating them. Keeping track of them is just some optimization, you can think of it that way. But the only reason they need it is because you need them to calculate the bounds on top of it, right? These are just concrete bounds. So they are not in terms of these variables. But again, so we're not going to calculate Li and Ui by doing interval propagation similar to what we were doing before. We are going to use the linear upper and lower bounds that we have already found to calculate Li and Ui. So Li and Ui in that sense are going to be a bit more precise than what we would get when we were doing the linear, when we were doing just simple interval propagation. And I have an example after this, which will demonstrate this.
Yeah, that can help.
Yeah. So are there any further questions or should I move on to the example?
I think you can move on.
Yeah, okay, sure. So okay, so this is the sort of example that I have, right? And this is again very this is directly from the deep poly paper. And I have written this sort of this light blue.
You can make, if you're able to make it a little bit bigger on
Sure,
this.
yeah. I think that will be good. Is this good?
Yeah.
Yeah. So the only thing is that of course I might have to scroll, but that is fine. Yeah, so there's this light blue things here. These light blue values here are actually the previous values, the intervals that we calculated previously, and I've kept here just for a comparison's sake to show how we are doing better here by using the deep poly domain, right? So so I have, I think, 20 minutes. So I'm going to go over this example somewhat slowly because I think
yeah, you have some flexibility. Because they assembled. I was going to say something. You have about 15 minutes more. I'm going to end and then, yeah. Although a couple of them keep on time, so for them it's extra penalty. Go ahead. You have till 5:15.
Okay. Sure. Okay, sure. So then I think I have yeah, I'll go.
For me, I have to stay till 6 o'clock anyway. So for the next shuttle. So maybe some people have to leave. You have to leave at 5. Yeah. Okay. So try to finish at 5 and.
Yeah. I think at least this example I'll definitely be able to cover by 5, and then at that point we can take up.
Okay. There's no.
So that is okay, right, sir? Yeah. Maybe I'll later on the Linson lectures I'll take some time off.
Yeah. I mean, you can continue with the next lecture. That's okay. Yeah.
Okay, sure, thanks. So here basically again, the input domain is what we're saying x1 and x2 are between -1 and 1, and that can directly be written in this form, right? So x1 is greater than -1, less than 1, right? So notice here that there is no linear upper and lower bounds because there is no previous layer variable. So you can think of so if I follow the notation from my previous slide, the AI is. So this AIL, AIU, these guys, they are like 0 in this case for the first, right, for the input. So that is okay. So now what happens in the next, right? So x3 is what? x3 is x1 plus x2. So though that immediately gives me upper bound and lower bound of x3 in terms of the previous layer, right? And then again, now we need to calculate what L3 is. So to calculate L3, there is the concrete lower bound of x3. What I'll do is I'll take the concrete lower bounds on x1 and x2 and then substitute them here and do basically interval propagation, right? So I get L3 is -2 and U3 is 2. So far, it's exactly the same as what we had before. And similarly, the same thing. We say that x4 is x1 minus x2. X4 is again, both greater than and less than x1 minus x2. And again, we get L4 as minus 2, U4 as 2, right? Because we substitute the concrete lower bound to get the concrete lower bound of x4, for example, we substitute the concrete lower bound for x1 and the concrete upper bound for x2, and we get minus 2, right? Similar to how you do interval calculation. So now you have ReLU, right? So what is going to happen in this case? So see, x3 is between minus 2 and 2. So I'm going to zoom in a bit on this diagram. Yeah. So on this diagram, right? So x4 is x3 is between minus 2 and 2, and we need to find some bounds on x5. X5 is ReLU of x2. Sorry, x3, right? So x3 is between minus 2 and 2. So this is already in this sort of third case, the non-trivial case of ReLU, right? And the upper bound is going to be this line, right? So this upper bound is going to connect the points minus 2, 0 to it's going to connect minus 2, 0 to 2, 2, right? And turns out that that line has got slope half. So if you calculate, it will turn out that that line has got slope half and y-intercept 1. So you end up with this particular bound for x5, right? Slope half, y-intercept 1 for the upper bound. Now for the lower bound, in this case, actually both of our choices are equivalent because, both of these two triangles are exactly the same triangle, right? So if I take this triangle, sort of this triangle and this triangle, they're both the same because for both of them, this is 2, this is 2. And over here also, this is 2, this is 2. So they're exactly the same triangles. So you can choose either one of them. And in the paper, they just, they make the default choice of saying x5 is greater than or equal to 0. But yeah, in general, you can choose, any one if both of them are the same, right? So this is what we get for the bound between these two things. And zooming back again a little. Similarly, again, this is exactly the sort of similar case, right? So we have x4 is between minus 2 and 2, right? So again, exactly similarly, the bound on x6 will be 0.5 times x4 plus 1, right? Okay. So now let's calculate this. And again, we take x6 is greater than or equal to 0. Yeah. So now let's calculate this concrete lower and upper bounds, right? So now when we're calculating the concrete lower and upper bounds, what they do is they will actually substitute this x3 with all of the variables and go all the way back. And again, there is some heuristic involved there. If depending upon what substitutions you do, you might get different bounds. One might be tighter than the other. But at least from what I can tell, their implementation, the heuristic that they do follow is substitute all the way to the beginning of the network, and that they seem to be showing the same thing in this example as well, right? So you have 0.5 times x3 plus 1, right? So what happens if we substitute this all the way? We get x3 is going to get substituted with this sort of an upper bound, right? x3 is again upper bounded by this expression, so we substitute that over here. So what we get is this is again less than or equal to x1 plus x2 by 2 plus 1, right? Now further substitutions here are not possible, right? With this expression is what we are going to now use to calculate the concrete upper bound, right? So x1, again, the concrete lower and upper bounds are minus 1 and 1, right? So to calculate the concrete upper bound with respect to this expression, we have to substitute 1 to x1. And similarly, we have to substitute. So maybe let me just make this a little bit bigger. Yeah. So we have to substitute 1 here. And similarly, we have to substitute 1 here because again, this guy is between minus 1 and 1. And what we get is a concrete upper bound of 2. Concrete lower bound is 0 because here this is directly going to tell you that x5. It's just simply saying x5 is greater than or equal to 0. So you can just say concrete lower bound is 0, right? But concrete upper bound comes out to be 2. Again, it's not different from the intervals yet, but the difference will start showing one more layer down the line. So any doubts so far?
Yeah, one question.
Yeah.
So if we had taken the other triangle, our L5 would have been different.
yes, our L5 would indeed have been different, right? In fact, our L5 would have been smaller, which would have been less, like it would have been more over approximate, less tight, right?
Yeah.
And that is in fact a very good observation. That is a, that you can say that is a problem with the current heuristic for choosing which line we would take, right? And again, in this paper, they don't actually address this. They just stick with these heuristics and then they show some experimental results based on this heuristic, right? But this is something
Diganta,
that,
I thought that they compare some area. So here,
yeah, they compare some area, right?
the same, okay, but still, if you're chosen the other one, you get
We
better.
get much something
Yeah.
that is worse. Yeah. So essentially here they're the same. So it should be equivalent no matter which one you choose, but they're not really equivalent because as this person pointed out, L5 is going to be different, and L5 is going to be much worse if you choose the other one, right? So in fact, I mean, even if they're not exactly the same, imagine a situation where the area of one triangle is just slightly smaller than the other, right? So maybe the area of this triangle turns out to be very slightly smaller than this triangle. Even then you end up choosing this line. But maybe although you're having a smaller area, the penalty you end up paying in terms of L5 becomes much larger, right? And this is in general a hard problem because, again, we are doing a series of calculations. We're doing a series of abstract transformations, right? We're making a choice here, and how that affects L5 and how L5 affects the choice of the the bounds down the line. That really depends on a lot of things, right? So very quickly it can get really complicated, and you can really sit down and come up with all sorts of heuristics and all sorts of situations where those heuristics don't work, right? So this is in general it's a problem, but and Alpha Crown actually solves this in a very interesting way. We'll come to that paper. I think a few more lectures down the line. I think maybe I'll cover. I'm not sure, but yeah, basically Alpha Crown is something that covers this, that solves this issue in a very interesting way. But yeah, you're pointing out a very important issue, I think, with this heuristic. Yeah, but for this example's sake, let's just say that things are nice. So if somehow you were lucky and you chose this line, L5 would turns out to be 0, and similarly L6 and U6 they turn out to be 0 and 2 respectively. It's exactly the same calculation here as well. So here also let me stress that we are substituting x4 to be again x1 minus x2 by 2. So we just maybe write that. And again, when we're calculating U6, we are basically using this expression and the bounds on x1 and x2 to calculate U6, right? Okay. So any questions, any further questions at this point?
No, you can go ahead.
Okay, sure. So now what happens in the next layer, right? So again, we have some linear layer, right? So in this linear layer, what we are doing is we have x7. x7 is x5 plus x6. So again, the bound for x7 becomes something like this: x is greater than equal to x5 x6 less than equal to x5 plus x6, right? Similarly for x8, right? But again, when we calculate this L7 and U7, these concrete bounds, we're going to do some substitution, right? So one thing that I want to mention is that if you look at it from the algorithmic point of view, you could have done the substitution directly when you're calculating the bounds, saying that we'll do the substitution while calculating this L7 and U7, and saying that this will do the substitution directly when we're calculating the bounds for X7 is actually sort of equivalent. It's just a matter of presentation, which way you want to say it. I'm presenting it this way simply because this is the example that is directly being taken from the paper. If you want to implement this, you can implement it the other way as well, and that actually might be a simpler way to implement it, where you only keep track of coefficient with respect to input variables. You don't even calculate, you don't even keep these intermediate bounds at any point. You directly substitute all this, right? So that's just some small point I wanted to make, right? Okay, so any case, let's come to the calculating the lower bound and upper bound for X7, right? So let's take the lower bound for X7. So again, we want to substitute these things. So let me erase a few things here. Right. Yeah, so we want to calculate the lower bound for 7, right? So we want to substitute x5 and x6 to do that, right? So we want to substitute x5 and x6. What do we substitute for? We substitute from here, right? So we say x7 is greater than equal to, so what is x5? x5 is x3 by 2 plus 1. What is x6? x6 is again x4 by 2 plus 1, right? And then again, we're going to substitute x3 and x4 from the previous things, which is again greater than equal to x3 is what? X3 itself is greater than equal to x1 plus x2 by 2. So we get x1 plus x2 by 2 plus 1 plus, again, x4 is x1 minus x2 by 2. Let me just maybe scroll down and make sure that I'm getting this correctly. X4 is x1 minus x2, and x6 is again x5 dot x4 plus 1. Oh, okay, sorry, I was calculating the one. Right? And now notice something. These two things cancel, right? So now we are actually have removed the dependency of x2 from our bounds. So what we get is x1 plus 2, right? And what was the bounds on x1? The upper bound on x1. The upper bound on x1 again is going to be 1, right? So if we substitute that here, what we really get is that it is less than equal to 3, right? So now notice that u7 is 3. It was previously 4. So if you had done just interval propagation, it would have been 4. But now it was 3. Now it is 3, right? So by keeping these linear expressions and doing this back substitution, we are able to get the fact that, look, this x7 is actually dependent on these two variables, x3 and x4, which are in turn dependent on the same variable x2, right? So there is some dependency between x3 and x4, which we actually end up factoring in when we do these two substitutions, right? Which basically cancels this guy and this guy's contribution. And because of that, we are able to get a tighter bound. We're able to get the bound x1 plus 2, which turns out to be 3, right? So we end up getting an upper bound of 3. The lower bound still turns out to be 0. I'm not repeating the calculation for the sake of time, but upper bound turns out to be 3. And notice that again, this is better than what we would have done purely by interval propagation. So any questions so far?
No.
Okay, yeah. So I think at this point, I'll essentially not go step by step for each one of those calculations anymore. You can maybe later on offline check that all of these calculations make sense. But I'll just tell you that the interval bounds, so the bounds for x8 end up looking like this, right? And then now notice that when L7 and U7 are 0 and 3 respectively, this ReLU is actually fixed to the active phase. So we end up getting x9 as to be exactly equal to x7, right? Which is again something that we did not have. I mean, so this again really tells us that u9 is equal to 3, which is again something that we did not have before, right? So this is a better bound than whatever that we had before, right? Similarly, here on the other hand, this ReLU does not get fixed. This is not fixed. This is still case number 3. So this still has got both upper and lower bounds. So we again have to say x10 is minus 2 and 2. So similar situation, 0.5 times x8 plus 1, right? And again, if you substitute and calculate everything, you get the bounds to be 0 and 2, which is again not much better than this interval, right? But simply because we have this situation now, where these two bounds are like this, we can directly get a much better bound for x11, right? So let's see, x11, again, when we do the substitution, we get x9 plus x10 plus 1, right? So x11 is then equal to x9 plus x10 plus 1. So now simply if we directly substitute the upper bounds from these two things, u9 and u10, right? We would again directly get something like this. So if we substitute u9 over here, we get that x9 is less than equal to 3, U10 over here, we get that X10 is less than equal to 2. And then we have +1. And that directly gives us that this is less than equal to 6, right? So notice that previously our bounds were 6. And even if we do nothing else, even if everything from this point onwards, we're not even doing any substitution anymore, just this improvement, or maybe I should say this improvement at this point, directly gives us some improvement over here. We get some bound to be 6, right? And notice that the particular property that we chose, which was, okay, maybe I'll just rewrite it over here. The particular property was that X11 is less than equal to 6. This is actually now proved, right? We're actually now able to prove this. Sorry, I think I scrolled up all the way by mistake. Yes, so this is directly proved, right? So this, just doing this substitution, factoring in the relations and getting this improvement over here has allowed us to now actually prove this property. Of course, here notice that we didn't do back substitution all the way. X9 and X10 we only back substituted up to one level, that is we back substituted with U9 and U10 directly. Of course, we could have instead substituted with these linear expressions and then substituted X7 and then taken X7 in terms of X5 and X6 and then substituted X5 and X6 and done this entire thing recursively all the way up to the first layer, right? And it turns out that if you do that, you get an even tighter bound. You get U11 to be 5.5 instead of 6. And I have written that calculation out in, I think, some of the next slides, if I'm not wrong. But in any case, I'll not do that calculation right now just for the sake of time. And maybe you can just sort of check that calculation offline. Unless you really want me to do it right now. So yeah, so this is the sort of idea, right? So the amount of back substitution you do can affect the quality of over approximation you get, the tightness that you get. But the example sort of motivates this, that even if you do one back substitution that factors in some sort of relation, then immediately you get like a tighter bound. Yeah. So any questions?
No, they all seem to be tired. No, they're all okay. So they're just.
Yeah. So should I?
I think this is a good place to stop because.
Yeah.
I mean, but make a note of anything that you might have missed, because you will be continuing. The next 3 lectures are by you, at least including this one. So you can plug in any holes that you have that you want to plug.
Yeah.
Okay?
Sure.
Okay. Thank you.
Thanks a lot.
I just wanted you to do those things, if you could.
The recording has stopped.